Hello everyone, I am Sabrina. Today I am going to talk about our paper, a pre-training framework that encodes noise information for speech quality assessment. And in this paper, I worked with my advisor, Professor Donald Williamson. And this paper is published in International Conference on Audio, Speech and Signal Processing ICASSP in India 2025. Speech quality assessment impacts the performance of several applications, including speech enhancement, automatic speech recognition (ASR). Speech quality assessment using deep learning procedure is tried to predict how people assess a given audio signal, and average user rating for a given audio signal is mean opinion score (MOS). So it tries to predict MOS score for a given audio signal. Many deep learning models have achieved success, but it needed large label dataset. And there is a scarcity of large label dataset in real world applications. Also, there is a domain shift problem. Self-supervised learning (SSL) can achieve similar performance even with a subset of labeled data. SSL approach are generally limited to extracting information regarding phonemes, speaker identity, emotion, but their performance on perceptual task is not as good because, and our assumption is that because it doesn't consider environmental factors that affect perceptual speech quality. So our goal, we propose a joint supervised and self-supervised noise aware pre-training framework that uses an encoder to learn information about speech and noise. We consider three additional classification and classification tasks for embedding noise. And such as signal to noise ratio, noise is added at different SNR, and correctly classifying the correspondent SNR for that audio signal. And the next one for category, a category of noise, category of background noise, correctly classifying in the category of background noise. And last of all, spectral energy distribution. That means noise is spread over the spectrum, and we divided the spectrum into three equal regions, and three equal regions: low, mid, high. The highest the region with highest energy is the target level for that given audio signal. So in this example, as the highest energy is located in low region, so the target level for this noisy signal will be low. And an additional target level is used for each worker for identifying clean signal. This is model architecture and pre-training and downstream task. For pre-training, we used existing encoder. One is problem agnostic speech encoder. Another one is popular one, mask encoder, and along with noise classification task. And for downstream task, later receives encoder representation and is trained for MOS prediction. In the right side, we can see the model architecture for problem agnostic speech encoder architecture. And first of all, the encoder and SSL task with other noise classification task. And I will discuss about SSL task in next slide. So this baseline encoder, problem agnostic speech encoder, is optimized with multiple classification or regression task to embed it low level and high level information. And high level information, that means speaker information and contextualization information. So encoder is consisted of 7 convolutional blocks, and workers is based on multi-layer perceptron. So here is regression task, classification task, along with a noise classification task. Baseline mask encoder is consisted of multi-layer transformer blocks using multi-head self-attention. We randomly mask 15% of the time frames during training. And we trained with a noise classification task. For downstream task, the downstream task for supervised regression-based MOS prediction and encoder is kept frozen during training downstream task. And for the mask encoder, masking is not performed during this stage. Range clipping helps to make sure that the value the predicted score in between 1 to 5. Dataset. Pre-training dataset clean. We took clean dataset for pre-training from Libri speech dataset. For noise, we used DCASE Community 2018 Challenge and other noise dataset like PNL Noise X 92. For downstream task, we use voice conversion dataset and NISCA dataset. Ablation study. So we remove certain baseline and proposed workers to assess performance, and performance is assessed with MAC and correlation metric such as LCC and SRCC. In the top of the table, it is a problem agnostic speech encoder baseline, and we remove one by one worker, and we can see that each baseline worker contribute to the overall performance. In the lower half, our proposed approach with existing encoder with noise workers, and we again remove one by one noise workers, and we can see that that removing SNR gives the best result. And this is the result analysis with other SSL approaches, and we can see like the top of the table is the other SSL, and the middle of that is mask encoder, and the last of the table is for problem agnostic speech encoder. So we can see that problem agnostic speech encoder with noise worker achieve best performance, and even with fewer parameters and a dataset size. And we can see that at addition of noise workers improve performance for both mask encoder and problem agnostic speech encoder. Among the SSL approaches, we can see like DASHENG performs well because it embeds as environmental information. And this result analysis is based on voice conversion dataset. And this result analysis is based on NISCA dataset. And we can also even see that at problem agnostic speech encoder with noise workers removing a SNR achieves best performance. The baseline one didn't perform. Problem agnostic speech encoder baseline didn't perform well because it is trained with only clean dataset. So conclusion. Our proposed approach generates embeddings that contain information about the speech and background noise, which are important to perceptual speech quality. So, an encoder containing information about both speech and noise is beneficial to perceptual speech quality rather than carrying only speech information. Result also showed that proposed approach performs well even with fewer parameters in comparison to multiple baselines. Thank you so much. Thanks to National Science Foundation and Ohio Supercomputer Center for your support. If you have any questions, let us know.